Hi everyone. In today's video, we're going to take a deeper dive into friction. As we're doing dynamics problems, we kind of want to remember to follow the prescription. With each dynamics problem, we're going to start with a free body diagram. We're going to sum our forces in the horizontal direction. We know that's the net force in the horizontal direction, so we can find the horizontal acceleration. We'll also do the same thing in the vertical, so we'll sum the forces in the y and set it equal to MAY. Now with that information and with the sum of the forces, we can rearrange at that point to find any of our unknown values. Okay? So as we look a little bit deeper into friction, we know friction is the interaction between materials in contact when materials are moving past each other or even attempting to move past each other. And we break friction into these two types. There is static friction and kinetic friction. Static friction is when the two materials are not moving relative to each other. So for example, when you're standing on a skateboard and you are rolling down a hill, well, gravity is making you and the skateboard speed up, but the interaction between your feet and the skateboard is a static type of friction because most likely your feet are not moving on the skateboard and you and the skateboard move together. So that's static friction because the relative motion between the two materials is zero. So we'll denote that with a second subscript here. I have force of friction, static. And then kinetic friction is maybe the more typical type of friction where two materials are rubbing against each other. If you rub your hands together, you know, that is creating some heat. Your hands get warm. So one thing that kinetic friction does is it converts mechanical energy into thermal energy. But we have kinetic friction anytime the two materials are moving relative to one another. Okay? If you think about what would make some objects have more friction than others. So maybe in your mind right now, imagine something that has a lot of friction. And you might think something like sandpaper or something that's really rough. So one of the things that friction is going to depend on is the materials that are involved. And it's actually the pair of materials that are involved. And we need some way to communicate that to our equations. Somehow we can tell the equations, hey, these are the materials that we're dealing with. And the way that we do that was with something called mu. So that is the Greek letter mu, and it is the coefficient of friction. So the coefficient of friction. And really what it is just a number that describes how much friction there is between these pair of materials. And if you, you look in a textbook for different coefficients of frictions for different pairs of materials. So wood on brick, wood on glass. There's going to be a coefficient of friction for each pair of material. So that's number one. The actual materials that are involved are going to affect how much friction we have, but also how hard the materials are being pressed together. So you might think about, okay, trying to slide a really heavy object like a refrigerator, and you might say that it has a lot of friction because it's heavy. That's not exactly how we want to look at that, because if, for example, someone was maybe lifting the refrigerator from above, maybe they have some kind of harness on it, and they take some of the load off, then it's going to be easier to slide. Well, that's not because the refrigerator weighs less, it's because it's not being pressed into the floor as hard. And we have a measure of how hard materials are being pressed into each other, and we actually call that the normal force. So we know that friction is going to depend on those two things, the materials and how strongly those materials are actually being pressed into one another. So the harder you press something into the floor, the more challenging it's going to be in order to slide it, okay? Now, I have these two types of friction, static and kinetic, and I think one thing we should establish is when you're trying to move something, maybe you're moving into your college dorm and you're sliding furniture around, do you find it more difficult to get something moving or to keep it moving once it's already sliding? If you think about that situation, it's a lot harder to get it moving. Once you get it moving and it has some momentum, you want to keep that momentum. You don't want to stop. You want to just get that furniture to where it has to go or get that object slid to where it needs to go, because it's a lot easier to keep it moving once it's already moving. And the reason is there are two different coefficients of friction. There's one for static friction and another coefficient for kinetic friction. So now every pair of materials has two coefficients of friction, one static and one kinetic. And if it's more challenging, to get something moving than it is to keep it moving, it's because the static coefficient of friction is greater than the kinetic coefficient of friction. Okay? And the other thing I want to mention, so each of these frictions is going to depend on the materials involved, so they're mu, and also the normal force, how strongly the materials are being pressed together. When we have kinetic friction, the kinetic friction is always found by doing mu Fn. So kinetic friction, as soon as you know that the materials are sliding past each other, instantly we know how to calculate that. We do mu Fn. Static friction is a little bit more interesting. I say that static friction is a reactionary force. It's reacting to the situation. For example, right now, if you just pushed on your notebook on your desk, if you only push with 1 Newton and it doesn't slide, something had to be pushing back against you. And if you draw the free body diagram for your notebook, of course it would have a weight and a normal that are balanced vertically, and also your 1 Newton horizontally was balanced with 1 Newton in the opposite direction. And that was static friction. Static friction didn't max out. It didn't go to its highest possible value and throw the notebook back in your face. All it did was try to keep the notebook in equilibrium. Again, if you press with 2 newtons, static friction is going to push back with exactly 2 newtons. And it's going to continue reacting until you overcome what we call the maximum value of static friction. So static friction, the maximum value is mu Fn, and it can be any value up to mu Fn. So as I push a little bit harder, a little bit harder, a little bit harder, static friction can continue to match me until I push over this maximum value, and then instantly the friction would become kinetic, and we could calculate that friction with mu Fn. Okay? The direction of friction is always going to be parallel to the surfaces, and one thing to keep in mind is that friction opposes the motion at the point of contact between the two materials. So it's always going to try to oppose attempted motion or actual motion between the materials at the point that the two materials are touching. So take a look at a couple examples. If you want to pause the video, you can try to do these free body diagrams. Number 1 is an object sliding on the floor to the right, and it's coming to a stop. And then the second one would be a car moving to the right and speeding up. Okay, if you're back with us, we'll draw the free body diagram of this object that's sliding. Keep in mind that we don't put velocities or accelerations on our free body diagrams, only forces. So I'm going to draw my object as a dot representing the center of mass. I'll start to draw the forces. Number 1, I know that we are always going to have weight unless you are really far away from any other object in the universe. We also have a surface on the bottom, a floor, that's keeping us from falling. So I'm going to draw a normal force that's in the opposite direction of weight, and it is balanced with the weight. And the last thing I'm going to do, since this object is sliding across the floor, it's definitely rubbing against that surface, and it's moving to the right, so we have friction in the opposite direction, and it would be kinetic friction to the left. Now I'm going to continue to go through this problem without numbers, but just to kind of go through the process of how I would answer a free response question. For example, one thing that it appears true based on this free body diagram, it looks like we would say that Fn is equal to Fg, and that's kind of universally understood, but I wouldn't want to start with that on a free body diagram, because I know that, or I'm sorry, on a free response, because I know in a free response question, I need to start with either a definition, a law, or something directly up from the equation sheet. And the definition of normal force does not say that it's equal to weight. There's no equation on the equation sheet that says anything about the normal force. So I need to show why Fn is equal to Fg, and I can show that by following my prescription. Number 1, I drew a free body diagram. Number 2, I'm going to sum the forces in both the horizontal and vertical direction. So I might take care of the vertical direction first, since nothing exciting is happening, or the net force in the vertical direction is 0. So when I sum the vertical forces, I get Fn minus Fg, because they're in opposite directions, and I know that that should be equal to MAY. Now, that is from the equation sheet. That is Newton's second law, net force equals MA. I also know here that since this object is moving horizontally, that the vertical acceleration is 0. So now it would be fair for me to say that Fn is equal to Fg. But I needed to show that. I can't just jump to that conclusion on a free response question. Next, I would sum the forces in the horizontal direction. So that's sum of the horizontal forces. And since I have only the force of friction against nothing, the net force is just the force of friction. Now, what I'm doing here when I sum my forces, I will always choose the winning side to be the positive direction. So I know this object is moving to the right. What I'm doing is I'm finding the magnitude of the net force. If I take that over to kinematics and I do kinematics with it, then I'm going to make sure that I take care of the direction of the accelerations and the velocities. But what I'm doing is finding the magnitude of the net force. So I'm saying that the magnitude of the net force horizontally is just the force of friction, and that is equal to mass times the magnitude of the horizontal acceleration. Again, if I find that horizontal acceleration, I know it would be negative. In terms of my forces, I've really already taken care of the direction by drawing the free body diagram, right? This arrow represents the direction. So I am treating it as a vector. I'm just finding the magnitude when I do the sum of the forces. Okay? So we know the force of kinetic friction has no choice. It must be equal to mu times Fn. So I could say that mu Fn is equal to max. And then I also know from my vertical forces that Fn is equal to Fg. So I could write that as mu k times Fg is equal to max. And then the last thing I could do is I could substitute mg for the force of gravity. So mu k times mg is equal to ma. And I would be able to tell you that the horizontal acceleration, interestingly enough, is independent of the mass, and it's just mu k times g. So for our object sliding and coming to a stop, the acceleration is just mu g. How about the second one, the car moving to the right and speeding up? This one might be a challenge. And if I were to give you a hint and say that anytime you draw an arrow for a free body diagram, if you can't name it, or if you can't come up with the agent of that force, it probably doesn't exist. So you probably drew a weight and a normal, and that should make a lot of sense. But then you may have been conflicted about what to do next. If the car is moving to the right and speeding up, one thing I know is that the net force has to be to the right. Right? The acceleration has to be in the direction of the velocity in order for it to speed up. So I know there's going to be a rightward force, and it may have had a challenge naming it. And if you're tempted to put friction to the left, I totally understand that thought, because friction does oppose the motion of an object. But I want you to remember that part at the point of contact. It opposes the motion at the point of contact. So in this particular case, it is friction that allows the car to speed up, right? Some people think that pressing the gas makes a car speed up. And well, really, if you lifted the car from the frame and you press the gas pedal as hard as you want, the vehicle's not going to move. It's not until you sit the vehicle down on the road and the tires are rotating that when they try to rub past the ground, then friction actually allows the car to move. So we need friction in order for the car to accelerate. Why to the right, though? In terms of that definition of friction, that it opposes the motion of an object, if you think about that's a terrible wheel. Sorry, if you think about the wheels that are in contact with the road, if this object is moving to the right, then which direction are the wheels rotating? Well, they would be rotating in a clockwise direction. And at the actual point of contact where the tires are touching the road, this part of the tire is actually trying to move left because of this rotation, this clockwise rotation. And if it's trying to move left past the road, then friction is going to oppose that motion and actually apply a force to the right on the tire. So we have friction that's allowing the car to speed up. And whether or not that is static or kinetic is going to have to do with how quickly you're trying to accelerate. Let's assume that this is a very responsible driver and they're not doing a burnout in which the wheels are rubbing against the road and you have all the smoke coming off the tires. And if they are driving responsibly, we would call this static friction. And the reason it's static is for every rotation of the tire, the vehicle moves forward exactly one circumference of the tire. If the situation were different, if you are pressing on the gas pedal too hard and the tires are rotating 6 or 7 times before the car actually moves one circumference, then we would have kinetic friction. And that's where we would see kind of smoke and things coming off the road. So responsibly, let's call it static friction, assuming this person is not over accelerating. Okay? There's one more example that I want to do, and these are what I would call qualifiers, in that it's not clear whether or not this should be static or kinetic friction. So we actually have to check first. And the way that we're going to check is we'll assume it's static friction until we find out that it's not. And then if we find out that it's not static friction, then we'll go back and do it as a kinetic friction type of problem. But the way that we can qualify it is by maxing out the static friction. So I'll go to the maximum value of static friction, which is mu Fn, and I'll determine am I asking for more than this value? If I'm asking for more and I'm not able to provide it, then I know it's going to become kinetic friction. If I'm asking for less, well, I know static friction can provide anything up to that maximum value. So in our situation here, we have a box it hasn't been strapped down on the back of this flatbed truck. So if the driver pulls away too quickly, it's going to slide off the back, or more importantly, the truck is going to pull out from under it if he pulls away too quickly. So I want to draw a free body diagram, and of course I start every one with a weight down, and in this case the normal is balancing the weight. So kind of again vertically we have nothing exciting happening, and well, something has to bring this crate along. In order for it to move with the flatbed truck, we would need friction pulling it to the right. And I'm not going to put a subscript yet because I don't know if it's static or kinetic friction. So from this free body diagram, I'm not going to go through exactly the way I would do for a free response question. I think in this case I'm just going to show that Fn would be equal to Fg, right? We kind of did that on the last slide, how we could prove that. And then I'm also going to say that the net force is going to be equal to the force of friction. Now that's true whether this is kinetic or static, because there's friction against nothing, so that is going to be our net force. We need to determine if that's going to be static or kinetic, and we'll do that by checking our maximum value of static friction. So we have the static coefficient of friction of 0.55 times the normal force, which we've shown is equal to the weight. So for an 80 kilogram object, that would be 800 newtons. And we can determine the maximum value of static friction by doing 0.55 times 800. So if you have a calculator, throw that in pretty quickly. 0.55 times 800, and I'm getting 440 newtons. Okay? So basically, as long as we don't request more than 440 newtons, then static friction is going to be enough to bring this crate along. If we request more than 440 newtons, then we can't provide it. So instantly it's going to become kinetic friction, and we're going to treat this problem a little bit differently. So I have the two scenarios here. If the acceleration were 5 meters per second squared, then I would say the net force, which is equal to ma. Well, if the mass is 80 and the acceleration is 5, then I would only need 400 newtons. So the net force in this case would be 400 newtons. I check my maximum value of static friction. I can go all the way up to 440, so I would have no problem providing 400 newtons. So in the first case, we would have Fn, Fg, and we would have static friction. Static friction is not going to max out. It's only going to do what it needs to do. So in this case, it would be 400 newtons, and it would provide an acceleration to the crate of exactly 5 meters per second squared. So it would keep it moving along with the truck. But if our truck driver is driving irresponsibly, or again, he forgot to strap this crate down, so this could be a bit dangerous. But if they try to accelerate too high, so the truck is going to accelerate forward at 6 meters per second squared. There's nothing stopping the truck from doing that. And if the truck were to accelerate at 6 meters per second squared, then we would need a net force of 480 newtons. Now again, we know that the friction is providing the net force, and our friction can only go up to 440 newtons. So what's going to happen now, since we're requesting an acceleration that's greater than we can provide, this crate is going to instantly, it's going to become kinetic friction. So now my free body diagram looks like this. We have Fn, we have Fg, and then we have now the force of kinetic friction, which is actually going to be less than 440, because remember, the kinetic coefficient of friction is going to be smaller than the static coefficient of friction. So we end up with a lot less friction than we could have gotten if we were driving more responsibly, and that means that the acceleration of the crate is going to be less than 6 meters per second squared. And if it's less than 6 meters per second squared, then eventually the truck is going to pull out from under the crate. And if you look back, if you're the driver and you look back, you see that the crate falls off the back. And I just want to be clear, the crate doesn't move backwards. It doesn't slide backwards. It's just that the truck is pulling out underneath of the crate faster than the crate is moving. So the crate still ends up to the right of where it started. It's going to land over here somewhere, but the truck is going to pull out from under it and it's going to continue moving, and eventually the crate's going to fall off. So because we have moved to kinetic friction, we are going to get an acceleration that's much smaller than 6 meters per second squared, and the crate's not able to keep up. Okay? So with those qualifiers, anytime it's not clear if it should be kinetic or static friction, we have to check. So we'll check static friction first, we'll max that value out, and we'll see if we're able to provide the requested acceleration. Okay, so I hope you enjoyed that video. Thanks for watching.